My name is Zhanhong Li, and I'm from the University of Shanghai for Science and Technology and University Shanghai, China. So today my presentation topic is electrochemical biosensing of interstitial fluid (ISF) biomarkers based on microneedle arrays. I feel very honored to be here to give this talk. And the main content of this talk is recent work carried out by our group. Just make an introduction. So why do we use microneedles? As we know, traditional blood sampling based diagnosis has some problems because the patients need to go to the hospital for blood sampling. So the patient will feel pain. Of course, they have the risk of get cross infection, and also in this process, it needs specialized equipment and also skilled operator. So if there's a way to provide minimally invasive sampling, it will be very convenient and have a lot of advantages. For example, patients, they can do self-monitoring at home. They don't need to go to the hospital. So they will avoid the risk of cross-infection. And combined with wireless transmission devices, and the doctor and hospital, they can remote to give the advice, medical advice to the patient. And more, if this technique combined with IoT thing, IoT, the Internet of Things, the big data analysis, and all artificial intelligence, so the patient can do the self health monitoring at home. So I think this way is has a very good potential for application. So why do we focus on ISF? As we know, the cells are immersed in ISF, and the ISF is a medium that the cells receive nutrients and secrete waste. So in ISF, there's a lot of biomarkers. If we can detect the biomarkers in ISF, so we can realize the health monitoring. But detect the biomarkers in ISF, there's a problem. As we know, ISF is beneath the skin. So there's a barrier, it's Zhanhong Li. So if we want to extract ISF from Zhanhong Li, it will be some difficult. So we need some tool, very powerful tool, like Professor Zhu told yesterday. We use the microneedle. We can see from this table, and there's a lot of biomarkers exist in ISF, and the concentration of these biomarkers in ISF is very good, convenient, relevant to the concentration in blood. So we can say ISF it can be considered as a substitute for blood sampling diagnosis. So this slide was showed yesterday, but I want to repeat it again here. And as we know, microneedle can be different material, for example, like metal, silicon, or polymer. And we can also design by different, we can have different designs, for example, a solid, hollow, or porous. And the single needle, the diameter of single needle is range from 20 to 80 micrometer. And the length can be from 150 to 1,500 micrometers. Actually, we can design, according to the purpose, we can design the different lengths. And we know the Zhanhong Li, the thickness is from 10 to 40 micrometer. So if you want to extract the ISF, we need to pierce the skin. And in this tips, we will feel no pain. It's painless, and actually it's minimally invasive. We can see from this picture, if we search the topic of microneedle in Web of Science, we can see from 2000 and to now, to last May, you can see a lot of publications grows very rapidly. So I think this is a very hot pot for this research area. So let's move to the research work. And this is our first try to use hollow microneedle array waveform for drugs detection in SF. As we can see from this figure, we use this design. And this patch has 4 microneedles, and each microneedle has a micro holes. And if we can fill the holes with conductive carbon paste or conductive silver chloride paste. So we can make this electrode as a working electrode, counter electrode, or reference electrode. And then we can modify electrochemical active material on the surface, then detect the targets. For example, in this case, we detect fentanyl and opiate nerve agent at the same time, and we get a very good response. So this is another try. We use this design to detect cholesterol. We can see the same with the previous work. We use hollow microneedle, and after we fill out the hole with the carbon paste and the silver chloride paste, and then we modified on the electrode, working electrode with cholesterol oxidase. We can detect cholesterol in SF. We can see from this figure we get a very good linear response. So so let's think about this. Actually, if we met microneedle directly as a sensing electrode, there will be some problem. If we use this to pierce the skin, maybe we will lose the active material. So the sensor will lose its sensitivity. So we try to solve this problem, and we directly make another sensing electrode. We use a screen printed electrode. And this work, we designed this electrode like a jellyfish. And we just directly put the SP screen printed electrode on the backside of the microneedle. And after the insertion of SF, we can detect corresponding biomarkers. For example, in this case, we detect uric acid, glucose, and pH. We can see different biomarkers response. And this is our another try, because we know if we use directly of the microneedle extract the ISF, also there's a problem. The extract amount is very few. Maybe it's not enough for screen printed electrodes sensing. So we try to increase this extraction amount of ISF. And in this case, we modified the microneedle, use magnesium chloride to give him the ability of osmic pressure. So under the osmic pressure, the extraction amount of acid will increase. So we can detect the corresponding biomarkers. The same with the previous work, we attach a screen printed electrode just directly on the backside of the microneedle, and we use the rat as a model, and we can see from this result the response of the target follow the trend of this change. And this work we detect urea and pH. So we have another try for hydrogel microneedle. Similar with the previous work, we directly put screen printed electrodes on the backside of the microneedle, and we realize the fentanyl sensing in ISF. So this is another interesting work we have done, and we can see from this figure we modified the microneedle use polypyrrole PPY to make it conductive. Then we combined with use reverse electrophoresis to enhance the illustration completely. And we can see from this SEM image, and the structure of this microneedle is porous. Porous have some advantages. Some big molecule, for example, protein, can immigrate from the needle to the backside of the platform. So after we attach the screening electrode on the backside, we can detect the protein. So in this case, we detect IFN gamma. And this polypyrrole modified electrode compared to the unmodified one, the amount of the amount of the illustration ISF is 2.8 higher than unmodified one. So we tried another interesting thing. We tried to combine our system to electrochemical material. In this case, it's a Prussian blue. We use this case. We use the enzyme here, GDH, to transfer the electron from glucose to the Prussian blue modified surface. And the Prussian blue, after the acceptance of electron, the Prussian blue will turn from blue to white. So the degree of this changing is relevant to the glucose concentration. So we can actually see use a different under different concentration of glucose. The color of this I think this one is different. If we use a smartphone to read RGB value and correspond this value to the concentration of glucose, we can directly read out the concentration of glucose. And we know that enzyme actually is very sensitive to the environment. And in this case, we try to use a non-enzymatic method to develop a biosensor for glucose. And this case is similar with the previous one. We use also the partially as electrochemical material, and the concentration is the same. It's relevant to the glucose concentration. This is the color, the dips. So also in this case, we use a smartphone to read out the RGB value, and we correspond to the I think it's not shown here. Correspond to the glucose concentration. So we can directly read out the glucose concentration. We can see from here the dips on the blue dips is different according to the glucose concentration. So this is also a self-powered glucose sensor. So finally, let's make a conclusion. Microneedle arrays enable minimally invasive ISF sampling, and if we use this approach, we can avoid the issues faced in traditional blood sampling diagnosis. And in our lab, we have different protocol or different methods to prepare microneedle arrays, for example, 3D printing and hydrogel. And we can design with different shapes, for example, hollow or porous design. All of these can realize the biosensing. And to solve the limitation of the problem of limitation of IS registration amount, we use osmosis and reverse electrophoresis method to enhance the registration of ISF. And if we use this method, actually we can realize rapid and active ISF registration. And of course, all of this method has been used for institutes sensing. Finally, we try some very new concepts of experiment, we use a zero power sensor. We combine it with microneedle arrays and Prussian blue to make real-time biomarker sensing monitoring devices. So that's all. Thank you, and thank you to all of our group members. Thank you.
Thank you very much. What question we have?
Please.
I'm wondering what other biomarkers you can measure in ISF that will be similar or correlated with biomarkers in blood.
Sorry.
So besides what you already shown, like
Yes.
glucose and
Yes.
fentanyl and others, are there other biomarkers we can
Actually,
correlate in blood and ISF?
actually, this depends on the, let's say, the modification of the sensor. If we modify the corresponding material, we can detect the corresponding analytes. Actually, this is just part of just few parts of the biomarker. We try more. We will try more. For example, irons and or another analyte or drugs. Actually, we can do everything. I think electrochemical. What electrochemical sensor can do, we can also do in this work.
Other questions? If no, thank you very much. It was a short and very interesting session. Thank you for.